Hi, welcome back to the Journey of Stars. I'm your tour guide, Luna. Have you ever wondered, while looking at the fancy galactic pictures taken by NASA, why do stars have different colors? Why do some of them shine brighter than others? Why is it when you look at the night sky, all the stars appear in a whitish glow? All these questions are essential to our understanding of the stellar evolution process. So before we delve into each specific process, let's first explore the general characteristics of every star to paint a bigger picture.
To begin with, let's first think about what makes a star unique. Color, temperature, chemical component, luminosity, as well as its distance from Earth are all key factors when we characterize a star. In fact, the different colors you see, blue, yellow, orange, are the result of their different temperature. Also, by analyzing the light emitted by stars, we can understand the chemical component of it. Furthermore, the way that some shine brighter than others are the result of their different temperature and distance from Earth. So, how does all of that work? Now let's have a closer look. The color of stars depend on their different temperature. The hottest stars emit blue lights, while cooler stars emit red lights. Why? Let's first look at how colors are produced. When you shoot a ray of light through a prism, you can see a rainbow of lights displayed. That's right, the white visible light you see is actually consisted of waves of different wavelengths. Those our human eyes can detect are interpreted as different colors: red, orange, yellow, green, blue, indigo, and violet. From left to right, the wavelength decreases. As frequency, the number of waves in an interval increases. According to this graph, a hotter star emits more of its light at shorter wavelength, which means that a blue star has more energy and hotter temperature. Vice versa, for a cooler star, it emits light of a longer wavelength, which means it tends to be red and has less energy. That's why we have blue stars like Spica, with a surface temperature of scorching 25,000 Kelvin, yellow star 6,000 Kelvin like our Sun, orange star Aldebaran in the Taurus constellation at 4,000 Kelvin, and red star Betelgeuse 3,000 Kelvin, the hand of Orion. But wait, why there are no green or purple stars? Those are the cute colors. Well, that's because green and purple are colors that our eyes cannot distinguish when they are compared with the rest of colors. Although the stars emit green light, purple light, and also a wide range of ultraviolet and infrared light, due to the characteristic of our human eyes, we are unable to identify those colors. Right now, most stars are currently classified under the Morgan-Keenan MK system using the letters O, B, A, F, G, K, and M, a sequence from the hottest O type to the coolest M type. Each letter class is then subdivided using a numeric digit, with 0 being the hottest and 9 being coolest. A luminosity class is added to the spectral class using Roman numerals, which distinguish giant stars from dwarfs. We will discuss this part later with greater details. Now let's look at some examples. Our Sun is a G25 star. Spica, the scorching hot star we mentioned earlier, is a B15 star. Bi253, an O25 star, located in a large Magellanic Cloud, is the primary standard of the O25 type. It is one of the most massive and most luminous stars ever known. On the other end of the spectrum, VB10, one of the coolest, least massive, and least luminous known star, is a primary standard for the M85 spectral class. The spectral classification system helps us better retrieve stellar information and compare a star with its billions of counterparts. Also, as we'll see later, it will help us better understand stellar evolution. Thank you for watching episode 3, part 1 of my series on astronomy, The Journey of Stars. Today we'll learn about why the color of a star depends on its temperature, why blue stars are hotter, red stars are cooler, and the standard MK spectral classification system. This episode is produced by me along with my project instructor, Mr. Decrado. If you want to learn more about how to use spectral lines to determine the chemical composition of a star, and to learn about the most important tool in astronomy, please make sure to subscribe to my channel and follow my coming part 2 on spectral lines and HR diagram. Enjoy your day and don't forget to keep looking out to the stars.